Welcome to my channel Too Irrational. I'm Pranay Sharma, and in this video we are going to solve the CS1 paper B conducted by IFoA Institute in April 2022. We'll see the detailed solutions, but if you want the solution sheet, I will leave a number below where you should WhatsApp or Telegram your email ID so that we can email you the solution sheets. Let's get started. Question number 1. An engineer is considering the maximum number of people who can occupy a lift. In particular, the engineer wants to assess the probability of exceeding a maximum weight when 8 people are allowed to use the lift at the same time, compared to 9 people. Assume that the total weight of 8 people chosen at random follow a normal distribution with the mean of 560 kg and the standard deviation of 57 kg. The total weight of 9 people chosen at random follows a normal distribution with a mean of 630 kg and standard deviation of 61 kg. Calculate the probability that the total weight of 8 people exceeds 650 kg, and for the second part, calculate the probability that the total weight of 9 people exceeds 650 kg, and for the third part, they are asking us to comment on your answers to part 1 and 2. At the beginning, all I have done is return all the given information. Let's go to part 1 where we have to find the probability. So P for normal distribution for 650, M1, S1, where we are saying that the lower tail would be false because we want the upper value. So the probability comes out to be around 5%, 5.7%. Then for the second part, we'll do the same thing. P norm 650. This time we'll take M2 and S2. Lower tail false, and we are getting around 37%. So for the comment, we'll say the probability that the total weight of 8 people exceeds 650 is 5.72%, whereas the same for 9 people is 37.15%. The chance that weight limit of 650 kg will be exceeded by 8 people is very low, but for 9 people is relatively high. Fourth part, calculate the interval for the central region containing 80% of the distribution of the total weight of 8 people. You can do this in two ways. We can say our 80% confidence interval. We'll make a vector. I have M1 minus Q norm. With one side we'll have 10% of the probability. Lower tail false, multiplied by the standard deviation, and for the other side I'll just copy this, paste, and instead of minus I need plus. So the confidence interval comes out to be this, and we have another way of doing the same thing. You can take the quantile value, so you can say Q norm. We want the quantile value 0.1 for the normal distribution with M1 and S1 as the parameters, and Q norm of 0.9 M1 comma S1. You can see we have exactly the same values. Assume now that the total weight of 8 people chosen at random follows a gamma distribution with the parameter alpha is equals to 96.522 and lambda is equals to 0.1724. Fifth A, calculate the interval for the central region containing 80% of the distribution of the total weight of 8 people in this case, and B part, comment on your answer to part 4th and 5th A. I have written the given information where I have taken alpha as A and lambda as L. I will use the quantile to find the gamma value. So we can see that the confidence interval is nearly the same. So we'll say the 80% confidence interval are almost the same, as the positively skewed gamma distribution will differ only in extreme values even though the sample size is small. So here I have commented on the sample size being small and the positively skewed gamma distribution, but still, because the confidence interval was much narrower, 80%, that is why we have not taken into account the extreme values, and gamma distribution will differ only in the extreme values. That is what we are saying here. Let's go to the next question. Question number 2, first A part, simulate a sample of 100 values from a beta distribution with the parameter A is equals to 3, B is equals to 1. Use the command set.seed 1 2 3 4 5 to initialize the random number generator before you start the simulation. B part, plot a histogram of the sample simulated in part 1A, and C part, comment on the shape of the histogram produced in part 1B. So first I'll just write down the data and then set.seed. We want 1 2 3 4 5. And we'll say our sample should be R beta. We want 100 values where the parameters are A and B. For the B part, we want the histogram. And let's write down a name. And here we have our histogram. We can see the shape, it is clearly negatively skewed. So we'll write that in C. For the second part, A, perform 1000 repetitions of the simulation in part 1A. You should compute and store the value of the mean of the sample for each repetition. Use the command set.seed 1 2 3 4 5 to initialize the random number generator before you start simulation. For this, I will first initiate the vector M, where I'll store the mean, and I'll say set.seed need 1 2 3 4 5, then a loop in 1 to 1000. We'll say our sample R beta, we want 100 values coming from A comma B parameter, then M ith value should be mean of S, and let's run this. B part, plot a histogram of 1000 sample means computed in part 2A. C part, comment on the shape of the histogram produced by 2B by referring to a fundamental statistical property. So I'll say histogram HIST of M. Let's write a name for this. So here we have the plot. Clearly it is symmetric, and we know why it is symmetric, because we are talking about the central limit theorem. So for the comment, we'll say histogram is symmetrical, similar to normal distribution. This is in support of central limit theorem that the sample mean of a large sample will follow a normal distribution. For the remaining part of the question, consider the following small sample of data given here in our code. So we can just copy and paste it. Determine a 90% confidence interval for the population mean of these data, stating any assumption you may take. So I'll run this data, and we will be assuming normal distribution. So you're saying assuming sample comes from a normal population. We'll calculate the x bar. It would be mean of y. We'll calculate the standard deviation. And we'll calculate the length. For the confidence interval, I'll use t-test. So I'll say test is equals to t dot test. I want y. Confidence level is going to be 0.9. I think that's it. I'll not require anything else. Say 90% confidence interval for mean test dollar confidence int. Here we have fourth part, determine an estimate of the standard error of the sample mean using the data. So the estimate of standard error would be our standard deviation divided by the square root of n. This becomes the estimate. Fifth part, determine an estimate of the standard error of the sample mean using bootstrap with a bootstrap sample size of 10,000. Use the command set.seed 12345 to initialize the random number generator before you start the bootstrap sampling. Here I'll say M2 is where I'm going to store all the means. Set.seed 12345. Then we will start our for loop. One is to 10,000. Here we are not going to assume any distribution, and that is why we'll be using non-parametric bootstrap. I say sample must be sample coming from y with replace true, and then I will store the mean. Say M2 ith value must be equal to mean of same p. Let's run this. Now the estimate must be standard deviation of these means, and it is nearly the same. Anyways, they have not asked us to comment on it. 6th A, determine a bootstrap 90% confidence interval for the population mean of Y data using the same bootstrap sample as in part B. So we are going to use quantile, and B part comment on the two confidence interval produced in part 3 and 6A. So we have the sample of mean, so we'll just say 90% of confidence, 90% confidence interval for mean, and we'll use the quantile from the sample with probabilities. We want 0.05 and 0.95, 5% on one side and 5% on the other side. So you can compare the original confidence interval and this confidence interval. They are nearly the same. So we'll say the confidence intervals in both cases are nearly same, but the bootstrap confidence interval is narrower as it is an iteration of 10,000 similar samples as Y. As the confidence interval are similar, the assumption of normality is valid. Let's go to the next question. Question number 3, consider a sample of 10,000 car insurance policies sold to drivers who have had a driving license for no more than 5 years. The data are given in the file carinsurance.rdata, which contains the following 4 variables. Because it is an rdata file, we will be opening it by right clicking and stuff. I'll just show you. But before that, always make sure that you are cleaning your whole environment, especially the global environment, so that we understand how many data points have been given to us. So here I have the file. I'll right click, open with RStudio. Yes, and here we have our data. So age, a factor taking the value of 0 for young and 1 for old. This refers to age of the policyholder. LY, the number of years the policyholder has had a driving license before the start of the current year. And NCD, the number of years the policyholder has had no claim discount before the start of the current year. And claims, the number of claims the policyholder submitted during the current year. It has been suggested that drivers belonging to the old age category have more years of no claim discount than younger drivers. First, plot two histograms for the number of years with no claim discount, one for younger policyholders and another for old policyholders. So for this, the data is 4 vectors. It would be better if we create them into a data frame. So I'll say data is data dot frame, and I will write them in the same order as given in the question, not here, this question. So age, LY, NCD, and then claims. Make sure the spelling is correct. And now we have the data here. Now we want to create a vector of NCD, but only when age is 0 and then only when age is 1, that is young and old. So I will calculate accordingly. I'll say NCD underscore Y for young should be data dollar NCD such that data dollar age is equal to 0. Comparative, that is why double equal to. And then NCD for old, same thing, data dollar NCD such that data dollar age is 1. Just to make sure that we have the correct values, I will see for age 0, my NCD was 4, then another 0 was here that had 3, then 5, and then 3. So for young, it should be 4, 3, 5, 3, seems correct. And for old, we had 4, 4, 4, 4, then 5, and then 3. So 4, 4, 4, 4, 5, 3, seems correct. Let's make the histogram for young. I will write the names properly. NCD for young policyholder, I want the same thing for old as well. So just copy paste and change it to correct. And here we have. So we were trying to see whether the old policyholders have higher NCD versus the young policyholders. That we can see properly here, that the young policyholders have NCD around 2 and 3, whereas old have more concentration around 4 and 5. For the second part, there's a comment on the suggestion that drivers belonging to the old age category have more years of no claim discount than young drivers. Use the histogram from part 1. So we'll say from the histograms, number of NCD years for young policyholders are concentrated around 2 and 3 years, whereas for old policyholders, it is concentrated around 4 and 5 years. Hence, we can fairly conclude that the drivers belonging to the old age category have more years of number of claim discount than young drivers. Third part, calculate the proportion of policyholders with more than 2 years of no claim discount among young policyholders and policyholders with more than 2 years of no claim discount among old policyholders. So the proportion is very straightforward. We'll say length of NCD young, where NCD young are greater than 2 divided by length of NCD young. So the proportion seems to be 57%. And same thing for old. Just change my Y to O. We have 97%. Fourth part tests the hypothesis that the proportion of the policyholders with more than 2 years of no claim discount is equal in both groups, young and old policyholder. For this, it would be better if I actually calculate these values separately. Okay, what I'll do is I'll say NY2 is equal to length of policyholder young that are greater than this, and NY, let's say it is length of NCD. Just writing this so that I already have these values. We can write it again, no problem. I'm just making it a little bit. So you can see we have the correct answer. I'm just making it a little bit more optimized, nothing else. Same thing I'll do. Instead of young, I want old. This would be easier because these values will be required in the next part. We'll run this to test whether I have done everything correctly. Yes, I got the same answer. Good. For the next part, I want to test. We'll be using proportion prop.test. For that, I will make my values ny2 comma no2, that is my x. Okay, I have written n02, it's no2, and n, we will take it as a vector of the total values, so ny comma no, and then we are going to do the proportion test. Prop dot test, we have x comma n. So here you can see the p-value is very small. I will write this as, let's say, test. It's nearly 0. So that is why we are getting here directly the value 0. So we'll say as the p-value is almost negligible, we have sufficient evidence to reject H0, hence the proportions are not same. An analyst assumes that the number of claims per year has a Poisson distribution. The analyst wishes to fit a generalized linear model GLM to obtain to the observed claim count using age, LY and NCD as explanatory variable. Fit a GLM to the claim count with age, LY and NCD as the main effect explanatory variable. So fifth part, we'll say model GLM, we have claims as our Y, then age is factor, so factor age, LY plus NCD. You can directly write this because these are given as our vectors, but you can also write data because I have written it as data, so it is data, and the family is Poisson. To simplify the integration of the model into business process, an insurer wishes to use only models with at most 2 explanatory variables. So determine which 2 explanatory variable out of age, LY and NCD should be used in a GLM for claim counts if only two explanatory variables are allowed. So here what we'll do is we'll create three models. And for comparison, we will be using the AIC number. So I'll write the summary. And the AIC number. So you can definitely use AIC number for comparison. You can also use ANOVA. I'll show you both of them. Here I'll need two more models. So I'll just copy this. I'll change each one of them. Instead of LY, I need NCD. Model 2, summary 2. Same thing with the third one. Here I don't need the age. CD and LY. Let's run both of these. We can compare the EIC. And we can say as the model with LY plus NCD has the lowest AIC, LY and NCD should be used. Next, if we are using ANOVA test, what we can do is we can make these models and we'll say we'll compare these three models. Now the degree of freedom has not changed, so we can just compare the deviance. The lowest deviance is what we will be choosing. So the lowest deviance here is the third model again. So we'll say the degree of freedom of all are same, but model with LY and NCD has the lowest deviance. Hence LY and NCD should be used. So again, so the same conclusion. Seventh part, comment on the comparison of the fit of the model in part 5 and 6. So for the 5 one, you can again calculate the AIC. Here you could and do the same thing. You can say you can compare the AIC. We know in the 5th part the AIC, and in the 6th part clearly we have model 3 has a lower AIC, and accordingly you can comment. Comparing the AIC, model with LY and NCD is a better fit, or you could definitely do the ANOVA test. Let's run this. Okay, I have written 1n extra. Now we can see. Now I do not prefer when we have degree of freedom as well as deviance negative. So what I'll do is I'll keep model 3 here, model 1 here. And because we do have a change in degree of freedom and change in deviance, I will say test want chi-square. Okay, I have written model 1. It should be model. Now if I run it, you can see yes, we have a chi-square value 78%. I can write this as test and then test dollar. I want the probability of the chi-square, so we have 78%. So you can say we do not have sufficient evidence to reject H0. Hence, model with LY and NCD is better fit. Let's go to the next question. Question number 4. An actuary produces the following summary of claim amounts and number of policies sold for 4 of her insurance client in the past 5 years. The policy expected to be sold in the next year, that is also given. Then they are saying the data of year 1 to 5 are given in the file claims.rdata, which contain this matrix and this matrix. Let's load it. So here we have the two matrix. The first part, calculate the estimates of expected value of m theta, expected value of s square theta, and variance of m theta under the assumption of empirical Bayes credibility theory model 2. Calculate the credibility factor Zi and calculate the expected claim amount for each of the 4 insurers in year 6. So it's very straightforward. There is no complications here. If you have solved a model 2 question, it is straightforward. You can literally copy paste all the codes from there. So the first thing I'll do is I'll just rename them so that it's easier for me to type. I will write data as claim matrix and volume as policy matrix. These are all the initial values that we require. N, that is number of columns, capital N, number of rows, X, that would be data by volume, XI bar, that is row sums of data by row sums of volume, PI, that is row sums of volume, P, that is sum of PI, and P star, that is again the formula. From the formulas, we can say this is nothing but our expected value of m theta. This is expected value of s square theta, variance of m. For the second part, we have to calculate the credibility factor Zi. Is going to be Pi upon Pi plus S by V. Third part, calculate the expected claim amount for each of the 4 insurers in year 6. So the credibility premium will be equal to this is our credibility premium. The new volume values given for the next year, we'll just write them down from the question. So we have 1920, 575, 2820 and 798. Then the expected claim amount, we'll say it is the credibility premium multiplied by the new volume. Overall, the paper was very straightforward, very simple, and I felt that it was the easiest paper that I have seen since 2019 when this R programming was introduced in CS1. But that just means the passing mark might go up, maybe 57, 58. The 1 hour 50 minutes given to us was more than enough to solve this paper, and I felt that there were not many places where we could get confused. So that's a good thing. If you find any mistake in my solution, please write down in the comment. I will pin them so that others can see them too. And like, share and subscribe this video. I will see you in the next one.